Hello everyone, my name is Avinash Narvekar and I am going to talk about optimizing solar installations. Here is a list of topics that we will be discussing today. First, we will look at the problems encountered in a typical solar installation, and then we will see how DC optimizers can help solve these problems, and finally we will look at some great features of Powerture's DC optimizers. So, let us start by looking at the problems encountered in a typical solar installation. Here is a drawing that shows a typical solar installation. It consists of 10 PV modules connected in series, or also known as a string. The combined output of the string is fed to a string inverter, which in turn feeds the power into the mains grid. Notice that the modules are all connected in series, which means that exactly the same current I flows through the outputs of all the modules. This is fine as long as all the modules are identical and generating the same amount of power. But what happens if that is not the case? Let us suppose the second module is partially shaded and generating less power than the other modules. But since we have connected all the modules in series, the same current still flows through the output of this module. It is quite possible that this current is much more than the current that this module can supply. What is going to happen now? Such a module that generates less power can pull down the output of the entire string. Let us find out how this happens. In order to understand this more clearly, we should first understand how PV modules behave. Usually, the behavior of PV modules is described using an IV characteristic or IV curve. The IV curve is a graph that shows how the current delivered by a module varies as a function of the output voltage. You can see that the current decreases slightly as the voltage is increased up to a certain point, and then it starts decreasing rapidly till it becomes zero. There are 2 points on the IV curve which are of particular interest. The first point is where the voltage is zero. This happens when the output is shorted. In that case, the current has a maximum value denoted as ISC, which stands for short circuit current. The second point is where the current is zero. This happens when the output is open. The voltage at this point is denoted as VOC, which stands for open circuit voltage. The power generated by the module can always be computed as V into I. If you consider the two extreme points, you will see that the power is zero in both the cases. When the output is shorted, V is zero. When the output is open, I is zero. So, the product of V and I is zero in both the cases. If we plot a graph of power, it will be somewhat like this. It starts with 0 and then it goes on increasing up to a certain point and then it reduces back to 0. Obviously, at some point in between, the power is maximum. This point P is known as the maximum power point or MPP. Let us draw a vertical line from P. The point Q where it intersects the IV curve is the maximum power point on the IV curve. The voltage and current corresponding to this point are denoted as VMP and IMP. VMP is the voltage at the maximum power point. IMP is the current at the maximum power point. Let us now see what happens when we have a string of PV modules. Here is a string of 10 PV modules. The voltages at the output of the 10 modules are denoted as V1, V2, V3 and so on up to V10. The current at the output of all the modules is the same. It is denoted as IS, which stands for string current. The IV curves of the 10 modules, they are shown on the top. We can use these curves to find out the operating point of all the modules. Let us see how. Since the string current IS is the same for all the modules, just draw a horizontal line corresponding to IS and find out where it intersects the different IV curves. The points of intersection are denoted as P1, P2, P3 up to P10, and they are in fact the operating points of the 10 modules. For instance, if we drop a perpendicular from P1 to the voltage axis, we find that the voltage of the first module will be V1. Similarly, if we drop a perpendicular from P2 to the voltage axis, we find that the voltage of the second module will be V2. Likewise, we can work out the voltages of all the 10 modules. The total string voltage Vs will be the sum of V1, V2, V3 up to V10. The string inverter receives the total voltage Vs for the string current Is and generates power Vs multiplied by Is. It tries to adjust the value of Is so that the product of Vs and Is is maximum. That is precisely the MPPT or maximum power point tracking done by the string inverter. If all the modules are identical and generating the same amount of power, the string inverter will ultimately draw the current IMP and the voltage output of each module will be VMP. The total string voltage Vs will be 10 times VMP. This is the ideal situation. But what happens when one of the modules is shaded? Let us find out. Let us suppose the second module is partially shaded. As a result, the IV curve of this module is modified. The current output is a little less than the other modules. If the string inverter continues to draw the current IMP, we find that IMP is more than even the short circuit current of the second module, so it does not intersect the IV curve of the second module at all. Where is the operating point of the second module now? In fact, we could extrapolate the IV curve to the left, that is for negative voltage values, and then we find that the IMP line intersects the IV curve for the second module at P2, and the voltage V2 for this point is negative. What does this mean? It simply means that the second module produces negative output voltage. This is really bad because now the power output of the module, which is a product of V and I, becomes negative. That means instead of generating power, the module starts consuming power. This also results in excessive heating of the module, producing hot spots that can cause permanent damage to the module. Modules are usually fitted with bypass diodes in order to limit the negative voltage. Actually, when a module gets shaded, the string voltage drops. So the string inverter realizes that something is wrong. It reduces the string current to a value Is dash lower than IMP. Let us draw a horizontal line corresponding to Is dash. It intersects the IV curves in points P1 dash, P2 dash, and so on. The voltage output V2 dash of the second module is now positive. So the module once again starts generating positive power. Isn't that better? Well, not really, because now at this level of current Is dash, the other modules are not operating at their maximum power point. For instance, the operating point of module 1 is P1 dash, but the maximum power point was P1. So it is not operating at the maximum power point. This is the case for all the other unshaded modules as well. That means all the unshaded modules will generate less than the maximum power that they could have generated. In short, we can say that when a module gets shaded, the maximum power point of that module is at a different level of current. But since all the modules are connected in series, the same current is made to flow through all the modules. It is therefore impossible for the string inverter to ensure that all of them operate at the maximum power point at the same time. Can we not do something better? Fortunately, the answer is yes. The solution is to use DC optimizers. Let us see how DC optimizers can help generate maximum power all the time. Let us see what a DC optimizer does. In short, we will refer to a DC optimizer as DCO. Essentially, a DCO is a DC to DC converter. It takes input from a PV module, does the DC to DC conversion, and produces an output that is connected to the string. The DCO is like an interface between the module and the string. The main purpose of the DCO is to ensure that the module operates at the maximum power point all the time. Let us see how it does this. As I said, DCO is essentially a DC to DC converter. It can reduce the output voltage and increase the output current. For instance, it can reduce the output voltage to half the input voltage and in the process double the output current. Let us take a specific example. Let us suppose the DCO's input voltage is 30 volts and it draws a current of 5 amperes. The DCO can convert this to an output of 15 volts at a current of 10 amperes. Notice that the input power is 30 into 5, that is 150 watts, and the output power is also 15 into 10, which is 150 watts. An ideal DCO works at 100% efficiency, so its output power is always equal to the input power. What is the effect of the DC to DC conversion? Let us try to understand this in terms of the IV curve of the module. The IV curve of the shaded PV module is shown in red. That's the input to our DCO. Assume that the conversion factor of the DCO is 2:1. So, at the output, the voltage will be half and the current will be double. The IV curve of the output is shown in blue. You can see that the short circuit current is now double and the open circuit voltage is nearly half. It is this modified IV curve that is seen by the string. So we must find the operating point using the modified IV curve. Let us suppose the string current is 10 amperes. Draw a horizontal line for this current. It intersects the modified IV curve at point P, and the voltage at this point is 15 volts. So the output of the DCO will be 15 volts into 10 amperes, that is 150 watts. The operating point at the input is different. Since we assume a conversion factor of 2:1, the current at DCO's input will be 5 amperes. Draw a horizontal line for 5 amperes. It intersects the original IV curve at Q, and the voltage at this point is 30 volts. The module will therefore operate at 30 volts 5 amperes. DCO is an intelligent DC to DC converter. It continuously manipulates the conversion factor in such a way that the module keeps operating at the MPP all the time. We considered the conversion factor of 2:1 only for the sake of example. The actual conversion factor will be decided by the DCO. What would have happened if the DCO had not been there? Since the string current of 10 amperes is more than the short circuit current of the shaded module, it would generate a negative voltage output. Bypass diodes would limit that to about -3 volts, but still the module would consume 30 watts instead of generating 150 watts. So we can say that the DCO has effectively increased the output by 180 watts, and that's a significant gain. We can summarize this by saying that a DCO ensures that a PV module works at the maximum power point all the time. It substantially increases the power output of partially shaded modules, and it prevents formation of hot spots and enhances the life of PV module. Let us now take a closer look at Powerture's DC optimizers. Powerture's DCOs are extremely compact, lightweight devices that work at a peak efficiency of 99.5%. They are compatible with all 60 cell and 72 cell PV modules of 250 watts up to 450 watts. They can also be used with half-cut modules. The MPPT algorithm used in Powerture's DCOs is completely transparent to the string inverter, so they can work with all standard string inverters, and they are far more economical than other DCOs, and it is possible to use them selectively only for those modules which are affected by shade.